Hello, Assalamu alaikum, and welcome everyone to our weekly J.Conway Spirited Mathematics Seminar series at LUMS. We are pleased to have today Dr. Imran Anwar from LUMS who would talk on a prelude to commutative algebra and its applications. Over to you, Dr. Imran.
Thank you very much, Dr. Shahina, for the introduction. And Assalamu alaikum, and good afternoon to everyone, and greetings of the day if there are different time zones. Okay, the discussion of this particular talk, and I have arranged it in a way where I can just go back and talk about commutative algebra from the historical aspects and some celebrated results to recall those. So I will be going in steps to brief introduction about commutative algebra and its application. And moreover, I will be discussing about some recently developed theories which evolved just a few years back, and just share a few words and thoughts on the open problems about those particular ideas. So let's start the presentation with this historical aspect that algebra, topology, and combinatorics are fundamental areas of mathematics, and moreover, they are considered historically. They are considered seems to be a different areas, but historically they benefited from each other. So one very important aspect is the theory of homology and homotopy theory in topology, where one applies the functor to translate the problem from topology to algebra and vice versa. Similarly, the concepts in algebra are inspired by combinatorics, in particular permutation group. So permutation group holds very important character, and this is going to be a very important, you can say, keyword of this particular talk. And in this way, the study of algebra is better understood with the help of the permutation group when associating it with the topology and combinatorics and vice versa. So one can say that permutation group plays the role of a bridge between these areas. And moreover, in the beginning, the algebra was focused on the study of polynomial roots finding. But in 17th and 18th century, the work of the mathematicians such as Galois, Cauchy, Gauss, Jordan, and Grassmann, they focus on the study of permutation group associated to the roots of the polynomial. So if you have come across the theory of Galois theory, which was introduced by Galois, it is all about the study of the roots of a polynomial with the help of the permutations. One very important aspect of the on the importance of the polynomial historically is due to the work of Weierstrass. And Weierstrass gave this particular theorem on polynomial function. According to the Weierstrass, every continuous function defined on a closed interval can be uniformly approximated as closely as desired by a polynomial function. That means for every continuous function on a closed interval can be viewed as a polynomial function, which can be due to this particular theorem, because polynomials are among the simplest function, and because computer can directly evaluate polynomials, so this theorem has both practical and theoretical relevance, and it has been used extensively in the literature. But these slides indicate the importance of the polynomial in mathematical analysis. Now, commutative algebra, if we talk, so this was all about algebra, but regarding to the commutative algebra, it is essentially the study of the rings. So you might have seen the definition of rings in your first year coursework of algebra and in algebraic number theory and algebraic geometry. So the subject initially known as ideal theory, and this was the initial name of the ring, which was coined by a German mathematician, Richard Dedekind, on ideals. Later on, David Hilbert introduced the term of the ring, what we use today. This is due to David Hilbert to generalize the earlier term, which is the number ring, which was introduced by Dedican. So Hilbert gave a series of results that laid the foundation of algebraic geometry based on rigor commutative algebra. Among those results is one of the most celebrated one, Hilbert basis theorem. It has a beautiful history that when Hilbert came up with the proof of the Hilbert basis theorem, so there was a mathematician whose name was Gordon. He was not convinced, and there was to and fro conversation between these two. And because he adopted very novel approach to prove Hilbert basis theorem at that time, which was not comprehensible. Nobody was nobody would follow that particular step. But later on, it became a trend in algebra. Later on, Hilbert came up with Hilbert null sets. With this is one of the theorem which is translating algebra into geometry. So and similarly geometry into algebra. So there are two versions of it. And then one important tool what Hilbert introduced it was the Hilbert series. And regarding to the convergence of those series, he gave this particular theorem with Serre, Hilbert-Serre theorem, which says that those Hilbert series, which are used for the classification of infinite dimensional vector spaces, is basically convergent when we are dealing with the finite K linear algebra, K algebras. In succession with the Hilbert strongly influenced Emmy Noether, and who recast many earlier results in the terms of the ascending chain condition. So Emmy Noether gave her part, contributed her part in the development of the commutative algebra, particularly the Noetherian structures. And Emmy Noether was, it is worth mentioning here, Emmy Noether was described by Albert Einstein as one of the most important women in the history of mathematics. And this is the modern phase of commutative algebra. If one looks at the commutative algebra, there are few keywords which was written, but the central part one can say about commutative algebra is the study of more or less is the study of the polynomial ring and operations on it. So modern phase of commutative algebra started with the work of R.P. Stanley, who was the first who used the concepts and techniques from commutative algebra in a systematic way to study simplicial complexes. So simplicial complexes was a very is a very important tool in topology, which is being used to classify. In other words, to give a topological invariant, which was basically introduced by Euler at that time, which is known as Euler characteristic. So it is used in topology for finding the homologies and classification, the Betti numbers of a topological spaces. But this was the first time that an algebra associated to simplicial complexes arise in the paper of R.P. Stanley, which is listed at the bottom. By considering the Hilbert function of Stanley-Reisner ring, whose defining ideals are square-free monomial ideals. So everything in this particular area deals with this polynomial ring, and the objects to study are the ideals, and particularly the ideals are generated by square-free monomial ideals. So Richard Stanley basically used the square-free monomial ideals to study the algebra associated to simplicial complex. And why did he do so? Basically, he was proving a conjecture, the upper bound conjecture. So in proving that particular conjecture, he built this kind of algebra. Since then, the study of square-free monomial ideals from both algebraic and combinatorial point of view has become a very active area of research. So if I say that due to this particular work, people started seeing the monomial ideal in the form of simplicial complexes. So whatever there was the abstractness in algebra, it was taken off by this work. So this commutative algebra is not a kind of abstract. So one can view those objects in the form of simplicial complexes. So modern phase of commutative algebra is basically Stanley-Reisner theory provides a central link between the combinatorics and commutative algebra. Pioneered in 1970s, the correspondence between simplicial complexes and square-free monomial ideal has been responsible for this for the development and progress of both the field. Among the most celebrated results are the Reasoner criteria for Cohen-Macaulayness. Okay, let me just tell you about this Cohen-Macaulay property. This is a topological property, and there is a central problem in topology as well as in algebra, which was I would say which was translated from topology to algebra due to standardized theory, is the classification of Cohen-Macaulay structure. So Reasoner basically came up with a criterion with the help of which one can classify these kind of things by using algebra. So this is the main core of this idea. And later on, by using the Reasoner's approach, Stanley gave the proof of the upper bound conjecture. And here comes another person who is very important in this story. His name is Hoxter. And Hoxter, what he did, he took these concepts from topology because the study was restricted only for scale-free monomial ideal, and Hoxter generalizes it for general monomial ideal. So there are, you can say, for scale-free monomial ideal, there is a combinatorial structure for whom one can study the topology and other things. But regarding to Hoxter formula, all these things generalize for arbitrary monomial ideals. And let's talk about little bit about Melvin Hoxter. He's an American mathematician. He's in Michigan, and he has established a classical theorem concerning Cohen-Macaulay rings, invariant theory, and homological algebra. So, if I would say that he is responsible of building a new branch of commutative algebra, which is namely the homological algebra. This is not wrong. He's the founder of that. So, here he is, and he is best known for his work on the homological conjectures. So, basically, his major contribution is, if you Google the homological conjecture, so you will the Google will open up a page with a list of questions what he formulated, and many of which he established for local rings containing the field, and the homological conjecture have been focus of research activity in commutative algebra since early 1960s. So this is one of the major project going on project on homological aspects of commutative algebra, whose founder is Melvin Hoxter. And there is a record of this in this particular paper of PC Robert, the homological conjectures. So who are interested in putting hand on those problems, so the list is available. The last person to mention here is Alexander Grothendieck. Alexander Grothendieck is considered by many to be the greatest mathematician of the 20th century. His research extended the scope of the field of commutative algebra. So he was a giant who was taking along all the tools from commutative algebra, homological algebra, built shift theory and category theory to its foundation. And he revamped the algebraic geometry's modern phase, and he applied the rigor commutative algebra into it. And he passed away in 2014, and there was an obituary which was published in EMS notices. If you would like to know about Grothendieck, so you can read this particular EMS notices. So this is all about the founder, how the theory was developed from person to person, and the celebrated personalities are there. Now here comes the real business of the commutative algebra. So during the era of David Hilbert, Hilbert was struggling in solving a system of equation. Okay, every one of you might have encountered the linear system of equation, and linear algebra is all about solving the linear system of equations. But what happened if one deals with the system of equation involving general polynomials, a polynomial in 5 variable, 6 variable, but they are not necessarily a linear system of equation. So how to handle, how to solve these kind of equation? So Hilbert came up with an idea, and he called it involutive basis at that time, but he could not come up with the proper technique of computing those kind of bases. And there was a hitch in that particular target, or you can say there was a bedrock in that, because there, the procedure involves a Euclidean division algorithm of the polynomial. And there was, everyone knows, every school kid knows that whenever you need to divide to polynomial in one variable case, you can divide it, you can find a pet remainder, and everything is fixed. But what happened in the case of two variable or three variable or four variables? So there wasn't any algorithm known till 1965. So 1965, Bruno Buchberger, in his PhD thesis, came up with the idea of generalizing the Euclidean algorithm, and moreover, he gave the concept of the Grosvenor basis what Hilbert was having in his mind by that time. And not only that particular concept, he also came up with the with an algorithm to compute those bases, what David Hilbert could not do at that time. And Buchberger named those bases after his advisor name, whose name was Wolfgang Grosvenor. And Grosvenor basis, together with the initial ideal. Initial ideal, just a quick view of initial ideal means, okay, you have a polynomial ring, and polynomial ring, there are ideals, and ideals are generated by polynomials. So regarding to every polynomial ideal, you have a K algebra, which is the quotient ring, a ring quotient with those kind of ideal. It has a K vector space structure. So initial ideals are basically the ideals which are monomial ideal associated to any arbitrary ideal, but the K algebra S quotient I and S quotient initial of I has the same K linear algebra structure. So this is a kind of computational ease one sees by using the Grosvenor basis theory, and they have been used not only for computational purposes but also to deduce theoretical results. So there are lots of results in commutative algebra based on this particular theory, and not only in algebra but also in combinatorics. So he's Wolfgang Grosvenor. Again, Emmy Noether is in the picture because he was an Australian mathematician and a student of Emmy Noether. So all the developments you can see that it turned out to be the same chain. So application part of commutative algebra, if I would say, so there are two kind of application. One should understand that one application is within the subject. So within the subject, you see that all the application of linear algebra is due to the power we are having to solve the linear system of equation. Many models, many problems, when you translate them, it turns out to be a linear system of equation. Then by using the matrices algebra tool, we are able to solve those problems. So one can say that linear algebra has a powerful subject with a lot many application. So what is this Grosvenor basis theory? This is just a generalization of it. When you are solving a linear system of equation, what about the system of equation with general polynomial? No restriction on the linearity. So I can say that linear algebra is a sub branch of this commutative algebra and Grosvenor basis theory. And this Grosvenor basis theory, also all the application you have seen regarding to linear algebra are in fact the application of commutative algebra, along with not only those, but solving the linear system, solving the system of polynomial equation. You come up with these kind of system when you are computing the intersection of surfaces and curves, finding closest point to the curve on a surface or to the given point, or Lagrange multiply problem. So it means optimization problems, they also include these kind of computation where Grosvenor bases are very helpful. So there is a book by Awong and Graffard, which is regarding to solving algebraic computation on a problem in geodesy and geoinformatics. So this is one of the applied area, which is a quite a sensitive area in the sense because geodesy is a science that accurately measures the understanding of three fundamental properties of the Earth. Number one, its geometric shape. Number two, its orientation in space. Number three, its gravity, and all the changes and properties with time. जो इसकी accurate measurement है, that is being done in geodesy, and there is a complete use of Grosvenor basis in solving algebraic computational problem in geodesy. So this book records all those things. And there is a website where the bibliography of Grosvenor basis is available. And in that, this is a very rich website in the sense you can find all application stuff which you are curious about Grosvenor basis. So everything is freely available and accessible to everyone. So this is a link for it. Okay, now I'm moving toward I'm done with the introduction part, historical part, and the development of this particular theory. Now I'm moving toward the theory of symmetric ideals. So this is one of the idea which was recently evolved, recently chain of increasing symmetric ideals have attracted considerable attention. Okay, this idea is not new. It existed, but it existed in other areas of mathematics, particularly in category theory, particularly in topology, where people formulate a filtration of a chain and then try to study the invariant from one step to the other step and look at the behavior how it is being studied. But recently in commutative algebra, the chain of increasing symmetric ideals have attracted considerable attention. And I will discuss some open problems concerning asymptotic behavior of several algebraic and homological invariant along such chains. So from here on, I'm going to enter into the main stuff of commutative algebra. Okay. So from now on, n denotes a set of natural numbers, C is an element in n, and k is an arbitrary field. Most of the time, we assume k to be an infinite field with characteristic 0. Okay, now we assume a ring R. So this ring is quite special with two indices, quite an unusual one, k and j. The first index is restricted in between 1 to c, and the second index is free from 1 to onward. So there is no bounding on the second index. So in other words, this is a polynomial ring in C cross n variable. Okay, our K. So this is a, or you can say that this is a ring of with infinitely many variables. Okay, and for each n, small n, coming from n, consider the following Nadine subring of R, where you are restricting this j from 1 to n. So how many variables are there? This is quite clear. This is a finite variable ring with Cn variables. So just like C cross n, so when you replace this capital N with small n, so these are going to have Cn variables. So this is a subring of this ring. Okay, it is useful to view R, this R, as a limit of the following ascending chain of polynomial rings. So R1, R2, up to so on, Rn, and then so on. So the limit of this particular chain is this particular ring R. By looking at this Rn, you can approximate, in other words, you can reach a limiting case of this R. Okay. Now let's talk about symmetric group. In the beginning of my talk, I said that I am going to discuss something about the permutation group. So permutation group, you might have seen that this is a group of all kind of permutation on n objects. So this is sum of n you have seen at your algebra course or maybe in combinatorics. This is quite this is quite popular, but this is a notation you might not be liking, that sim infinity. So it means that it clearly indicates that you are going to permute infinitely many elements, but definitely in order to define it, so it is defined in this case that you are going to take the union of all these sim1, sim2, sim3, and then so on. So this is not the usual symmetric group you have seen, but this is the union of all these. So in other words, union of all. So it contains sim1, sim2, sim3, symmetric group of one object, symmetric group of two objects, three objects, four objects, and n objects. And this is quite common. The persons who are familiar with dealing with combinatorics, that symmetric of n object is the same as the stabilizer of n plus 1 in sim n plus 1. That means you fix the place of n plus 1, and then you allow all kind of permutation of first n object. So one can also view that
Dear
sim.
Imran,
Yes, yes, yes,
Imran,
yes.
may I ask question? So what is the binary operation in this group sim infinity? So
Okay.
how you define?
Oh, okay. This is a very good question. Somehow, n at the moment I'm not using any binary operation on it. I'm just considering it as a collection of all these kind of objects at the moment.
So how it becomes group actually? So what is the binary operation? That's something.
In fact, this structure is coming through this particular idea. So that's why this is a kind of this is a valid question, because you can't multiply sim1 with sim2 element. Yani, in other words, कि अगर मेरे पास permutation है 5 elements की, so I can't multiply it with 6 element. But
Okay.
the things are working in this way. That
Okay.
means, for instance, okay, try to understand. For instance, I want to multiply sim5 element with sim2. So I will not do anything here. I will consider sim2 की जो embedding उसके अंदर आ रही होगी sim5 में.
Okay.
You understand? So it is embedded somehow in sim5. So I will do everything in sim5.
Okay.
By using this union structure, so I use this particular embedding to perform the algebraic operations.
Okay. Thank you.
Is it clear now? Is it clear now? So instead of restricting to 2 variables, so I will always go with the bigger one.
Okay.
So in every case. Okay.
Okay.
Okay. Okay. Now, the persons who are familiar with the direct limit case, this is a structure just like directed system. So in directed system, you always perform the operation in the bigger index when you are dealing with it. So this is a kind of directed system, right? Okay. Action of infinite symmetric group on R. Now this is here comes a real game. So you have seen R, the polynomial ring with these indices K and J. Now we are going to apply the group action on this R, on this ring R of this group, and how it is going to act. Consider the action of sim infinity on R by acting on the second index of the variable. That means, so if there is a sigma, a permutation which is coming from sim infinity, from xk, it attacks on a variable xkj, so it will simply attack on the second index sigma j. So it will leave the first index as it is and attack the second one for sigma belonging to sim infinity. Are there some questions? Let me just check. Okay. Okay. So, okay. So this is the way the group action is going to be defined. So I hope the group action is clear to everyone. Or okay, if you would like to see this particular group action on Rn, so you restrict sim infinity to sim n in n variable case. So in mathematics, when we have a directed system, so directed system is studied in the way that at which level you are studying it, bring the thing to that level to get it resolved. So okay, same is the case. Sim n is acting on Rn, and we say that. Now this is the definition.
So Imran,
Yes.
is this R okay? So another question: is this Rn homogeneous? I mean, is this action transitive?
Sorry, what about
So
this?
so you say that this action of sim n on Rn is so we
Yeah.
have the action. So my question is this Rn homogeneous space then? By
No, no, no,
homogeneous,
no,
I
no, no,
mean,
no, no, no,
is
no, no,
this action
no, no, no.
transitive? Mm-hmm.
You mean the action is? Say it again.
Transitive.
Transitive.
So so we have the homogeneous space when the action of a group on that space is transitive. So by transitive, I mean if you take two elements of this space, let's say Rn, which will be, I guess, polynomials. So is there a way if we can connect those two polynomials by the action of the same n or maybe same infinity? So if we can do this, then
probably yes,
this
probably
space
not, but
will be
I'm
homogeneous.
not sure. I'm not sure about
Okay.
it. Probably because it requires some working. I didn't notice this question. Probably it is true. Probably. So,
Okay.
but in Rn case, you can simply think of it as so. Applying the sim operator means you are just relabeling the variable. So maybe you will see in an example. So you are
Okay.
just relabeling the variables in the case. So this is just a relabeling of it. Okay, now the interesting part is that so this structure is quite a vague structure. You can see that the structure is of R is like this one. This is the way to look at R. Rather than this one, we prefer to look at in this way. So any ideal in R is going to have these kind of label I1, I2, R, In, and then so on. And we say that an ideal in R is same invariant, same infinity invariant, or same invariant for short. If you apply this sigma operator, that means a permutation operator, which is a member of same infinity on any member of I, so the resultant polynomial after the change of the variable will also be a member of I. That means if you look into this case, for instance, you apply some sigma here, so you probably whatever you are doing, it is taking it to further level. So everything is appearing inside this particular structure. So if an I is receptive to the sigma setting, so we say that this particular ideal is sim invariant ideal. You will see in an example soon. In order to investigate such ideal, a natural approach is to consider the truncated one, what I was describing just right now. So viewing the ideal in this case, so I intersection R, and you can have a filtration I1, I2, I3, and then so on in the same case. Or note that the sequence of truncated ideal In, which is also known as in algebra, commutative algebra, we also call them the filtration, forms an ascending chain, and furthermore it is a sim invariant in the sense that if I apply sim m, okay, probably this will give you more clarification the कि जो अभी आपने question पूछा था. If you restrict sim m and in, and m is greater than n, so you understand when I say in, it means uh, I is involving n variables. So there is no n plus one variable there. You understand regarding to the second component. When I apply
Okay.
sim m on it, where m is greater than n, so I'm applying a permutation जो उससे बड़ी है. So
Mm-hmm.
I will view it in im. So it will be viewed in im. So I take this inth part in im, and then I view it in im. So this is going to be in im. Definitely, because you will see in an example where I can elaborate this thing more in the upcoming example. So conversely, the scene is this: you pick any truncated, you pick any filtration of semi-invariant chain. So its limit in R is this particular union. So this is the other way around of doing it. So this is the way from truncated to reaching to the original ideal, and this is the way you have a truncated system. So its limiting case is giving you the picture of the ideal. So ideals in this particular structure are this one. They look like this one. So they have a filtration structure and they have this kind of form. Okay. So although R is not a Nadine ring, so everyone who is familiar with the Nadine structure, so in the polynomial case, if the ring is the polynomial ring is having finite number of variables, so this is Nadine, and this is the famous Hilbert basis theorem saying the same. So a number of useful finiteness results have been established for this ring. So definitely, uh, this particular ring is not Nadine, but the surprising fact is that a number of useful finiteness results have been established for this ring. For instance, it is known that sim-invariant ideals in R satisfy the ascending chain condition. So the ideals who are sim-invariant mean this one, who undergoes this particular change and satisfy this particular condition. These are sim-invariant ideal. You have seen the definition. And for this ideal, the ascending chain condition verified. So any ring in which sim-invariant ideals satisfy the ascending chain condition, they are called the sim-Nodinian ring. So there is a modification of symmetric Nodinian ring. This particular terminology was introduced by D.E. Cohen And while he was working on metabillion varieties, on the laws of metabillion varieties, in this paper, he proved this thing that your sim-invariant ideal satisfies the ascending chain condition. So this is a celebrated result. And this was first discovered by Cohen in his investigation of the variety of the metabillion group. So this is a modification of the Nodelian structure of this particular case. Now, based
हेलो
on, sorry,
इमरान, कोई एक एग्जांपल बता सकते हैं जो सिम
uh,
नोथेरियन ना हो?
Josim Nadine now, these I didn't include that example in my slides, but I can I will share the references there are where there are ideals which are not sim Nadine.
ओके, थैंक यू.
Okay, the celebrated result. Okay, so research aspect of the symmetric nonlinear structure. So let's talk about the real business, what people are doing with this kind of structure. So sim nonlinear structure was this particular concept was first taken up by Uwe Nagel and Tim Romer, and they introduced a Hilbert series of sim-invariant chains. And this is just generalizing the typical Hilbert series structure, what is well known for general Nodelian ring structure. So they introduced the sim-invariant chain structure Hilbert series for these kind of ideals and show that they are rational functions. So in other words, they prove the famous Hilbert-Serre theorem version for this particular case. So this is the exact statement of Hilbert-Serre if one take of the sim case here. So they prove the similar result for sim-invariant ideals, chain of ideals. As a consequence, they determine the asymptotic behavior of codimension and multiplicity because these terminologies, particularly the multiplicity and codimension, these are based on the rational form of the Hilbert series. Once they fix this thing, so one can talk about these two algebraic invariant. So this kind of okay, for those who are not familiar with this result, so just a quick note on multiplicity. So whenever I say that this is a rational function, so rational function mean this is going to be something, a polynomial appearing in the numerator and a polynomial appearing in the denominator. So the polynomial which is appearing in the numerator, it has a special character that for instance, I say that this polynomial is in t variable. So Hilbert series is found in t variable case. So if it is in t variable, so p of t, the polynomial which is appearing in the numerator, p of for this particular polynomial, p of 1 is not equal to 0. And when you replace t with 1, it will never give you a 0. So this, so whatever you get when you put t is equal to 1 in the polynomial appearing in the rational function of the Hilbert series, that particular number is called the multiplicity. So this multiplicity is that particular number. So once they fix this thing, then they jumped into this particular problem. So as a consequence, they determined the asymptotic behavior of the codimension and multiplicity. So asymptotic mean you are going along uh, this particular chain. So for the ideal, this is I1, I2, I3, and so on, IN. So at I2 level, there is an ideal, then I3, there is another ideal, I4, there is another ideal, and I2 ideal is in R2, I3 ideal is in R3, IN ideal is in RN. So at every step, you are working in a finite setting, what you are used to in usual commutative algebra. And now for I2, one can compute the multiplicity in R2. Similarly, for I3, one can compute the multiplicity in R3. Similarly, for IN, one can compute the multiplicity in RN. So the interesting part is to see that asymptotically, when you are moving along up till infinity, how the codimension and how the multiplicity behave. So the study of the behavior of algebraic invariants along these chains is basically the purpose of the research the people are doing at the moment for this kind of structure. So we were here. So they discuss the semi-invariant chain that codimension and multiplicity, and what they found, the codimension grows eventually linearly, So it has a linear nature, and whereas the multiplicity goes eventually exponentially. So it has an exponential behavior. Yes.
एक irrelevant question है इमरान.
Yes.
उनकी जो हिल्बर्ट सीरीज की कैलकुलेशन थी कितनी एक्सप्लिसिट है? आई मीन लाइक
This is a very good question and very deep question. In fact, for these kind of computing, they have to build the new formulation of all these theories, existing theories. And this is quite the computation is quite extensive, because you have to handle this growing variable structure. So you will see what they were. I will reveal few of the computational part. So how the thing grows. In fact, for algebraic geometry, the beautiful part is that you can pick any ideal. So you can work with any ideal. For any ideal, you can build this particular chain. You started with 4 variable, 5 variable case, and you can extend and formulate this filtration and do these kind of computation. So building these kind of ideal is not a big issue. So there is a particular way of doing so. I will show you in a moment.
okay,
Okay,
thanks.
so their work ultimately lead to this general problem. So this is a problem which was which was discussed in a latest survey on these kind of structure, which is by Kovetsky, Lee, and Tim Romer again in the picture, study the asymptotic behavior of invariant along some invariant chain of ideal. So regarding to invariants mean, you can talk about, so they discuss about multiplicity and co-dimension. So one can talk about any algebraic invariant. So keep on investigating the chain of so algebraic invariant. Keep on changing the type of the ideal. So you are coming up with the new problem, and this is a new study where people are interested at the moment. And this area is widely open, and this is recently evolving things in commutative algebra. Okay, there was one challenging situation. Okay, if I talk about algebraic geometry and the use of Grosvenor basis, one has to deal with the initial ideal, because the computational part in commutative algebra or in algebraic geometry is it goes through the initial ideal. So for any ideal I in R, the sim invariant ideal, I assume that I is a sim invariant ideal. That means I is generated by some polynomials, and those polynomials are satisfying the property of the sim invariant ideal. So that undergoes any change, so they remain inside that particular structure of with the truncation, with given truncation is this one. A useful technique for investigating the asymptotic behavior of the chain is to pass to the chain of the initial ideal. Just this is one thing which is quite common, known. The computing part of algebraic geometry deals with, instead of doing the computation for the original ideal, people always prefer to deal with the initial ideal. But there was an issue, and issue was that original ideal was sim invariant, but when one computes its initial ideal, the truncation chain of the initial ideal, unfortunately the chain does not behave well. So it is typically not sim invariant. So there are counterexamples given in the references I will share at the end. So there you can see these typical problem. So in order to handle these kind of challenging situation, so there was a change in the sim operator they come up with. To deal with this issue, there was a need to look for another action on R which behaves better with respect to the monomial order. Uh, I I didn't include the monomial ordering fact, but the persons who are familiar with the commutative algebra, they knows that the computing of the initial ideal is a business which is based on the monomial order, and one has to do these switching of the variable in order to take that can take care of this monomial order. And in order to handle this situation, Tim Romer and Uwe Nagel, they come up with this kind of before, even before them. So there was an order which was introduced. So this is not the usual symmetry operator. Instead, this is a strictly increasing function on n. It says that you are again talking about the permutation. Again, this is going to be a one-to-one function or permutation function, whatever, but it is restricting that two adjacent entries, j and j plus 1, they map on some elements which also following the same inequality. That means the image of j plus 1 should not fall before the image of j. So this is one of the operator that simply handling the terms ordering or monomial ordering of monomial ordering of of the issue what we were facing in the previous slide. So this is so to deal with this issue, one has to take care of the action which behaves well with respect to the monomial order, and this is a kind of operator which is behaving well, which is preserving the monomial order. So whatever the monomial you have this kind of operation, and after the operation, the new monomials they are taking care of. They are also following the same monomial order which was mentioned in the starting. So analogously of sim infinity, one can apply. So instead of taking the operator from this group, one restricted to this one is a monoid, and on R and this application. So how to apply inc is the same way like sim operator was operating. So you just plugging the pi to the second index and computing the same way. But this time this pi is not coming from sim infinity; it is coming from inc operator, strictly increasing operator. And there is a definition which is an equivalent definition of the sim invariant ideal. So now we have invariant ideal. So the definition is the same, that pi of f should be for all f of I should be inside I. So this is almost the same definition, and it has a variant which is not so interesting at the moment to study, but there is another study which is linked with m and n. When we have mn, this kind of structure, what is this inc mn operator? It means that for a fixed number pi m, so this is a bit weaker condition than the original one, that pi m it restricted that so it restricted that your pi m should be less than n. So whatever is happening on the other places, it doesn't care, but it fixed the two number m and n, and they should follow this pattern. So for the rest can follow any pattern. And in fact, this kind of operator is also studied, and this operator also respects a kind of monomial ordering, but the actual one is this one which completely care. I think this will not take care of the monomial ordering, but this does. Okay, let's discuss an example. So I pick a page writing example because somehow it was easier for me to, because I had a written example, but the things were not conveying. So I think of presenting an example in the way so that you can understand. Okay, consider any ideal. For instance, I pick a very simple ideal x1, which is generated by x1, x2, x2, x3, and x1 square. So this is a simple looking ideal. So applying inc operator mean I am giving the input I3 and applying this particular ideal. So this is a simple case of inc. So I'm assuming that my k component is 1. So in this example, the usual setting, your k is 1. So you are not taking care of that there are two kind of indices. You are assuming only one kind of indices. Okay. So this is a simple case, simple setting. I gave an input I3. So, okay, let's talk about the inc operator possibility. When I say that the inc operator is operating from n to n, in general, the things are moving from, because this is what why I have written I3 here, because it is this ideal is described in 3 variable case. So that's why I mentioned I3. So inc operator behaves like this. You are keep on increasing one variable. So what will, from I3, I need to obtain I4. So I have to build that filtration at my own. So moving from 3 variable to 4 variable case, I will use the inc operator in the way either I can fix all the maps 1, 2, 3. So still it is satisfying the condition of inc that 1 is less than 2. So does 1 is less than 2 here. Similarly, fixing this 1 and 2 goes to 3, then 3 has to go to 4. 3 can't go to 2 due to the condition of inc. So this is another operation I'm having from 3 to 4. Similarly, there is another. 1 and 2 is fixed, but 3 sends to 4. Similarly, if I move 1 from 2, then 2 has to go to 3 and 3 has to go to 4. And under this particular setting, when I give this particular, apply this particular operator on I3, so this is the identity sort of operator, so it gives me I3 back. When I use this particular setting, so 1 goes to 1, 2 goes to 3, and 3 goes to 4. So I have to change 2 and replace 2 and 3 with 3 and 4. So x1, x2 will go under the change. So in this particular setting as x1, x3, so 2 replaced with 3, and 2 replaced with 3, and 3 replaced with 4, and x1 square stays as it is. Similarly, this process, so I have to consider all the possibilities. For instance, if somebody didn't pick, let's see this one. So 1 goes to 2, 2 goes to 3, and 3 goes to 4. So wherever there is 1, replace this 1 with 2. Replace this 2 with 3, and replace this 3 with 4. And you come up with these generators. Now, what is your I4? The next ideal in the iteration, in the filtration, this is going to be the union of the generators of all these. So I3, so all the generators of I3 plus the generators which are not present in I3, they are the new one. So X1, X3 is not there. So a new entry, X1, X3, X3, X4 is not there. So it is a new entry. X1, X2 is already there, so it is not going to, because it is already included. X2, X4, it is not there, so it is included here. Similarly, X1 square is already in I3, so there is no need to write it. X2, X3, X2, X3 is already there in I3, so there is no need to write it down. X3, X4, I didn't take care that X3, X4 is already included in this part, but that's why it is mentioned twice. So there is, so the people who are working in algebra, they know there is no mistake, so it will be reduced to one case. So minimal generator, in case of minimal generator, I have to skip this entry and end up with this one. So this is the way I formulate I4. Similarly goes on for computing I4, I4 I have computing I5, I6, I7, and then so on. So from this ideal, I get this ideal, and from this ideal, again by using the inc operator from 4 to 5, I got I5, and similarly from applying inc operator on I5, I got I6, and this is the way you build an ideal. Okay, now the real business in commutative algebra is that you pick any ideal or any class of ideal and do these kind of computing and build these kind of filtration and study any algebraic invariant you would like to study in this kind of the way Tim Romer and other Uwe Nagel has done, and this is going to be contributing into this particular theory. And the people are interested in looking at the behavior, how the algebraic invariants behave asymptotically when one study this kind of structure. Okay, now I stop here at the moment if there are any confusion regarding to the example. And now you see how the people are building these truncated chains. So it is not going from up to down, it is going from down to upward. So the build-up is this one. So any questions so far? Okay, if there is no, so let's move to the next one. I conclude this talk here with the following fundamental finiteness theorem, which was given by Hilar Campo, which was published in 2013. And this says that the ring R is inc-Noetherian. Now you understand sim-Noetherian and inc-Noetherian. That is, if inc-invariant ideal R, there exists finitely many elements. If there is any inc-invariant ideal, so there will be finitely many elements F1 to Fm in R, such that you can generate this ideal by applying inc time and time and time again, the way I was doing it. So you understand? So I was applying the inc operator on each generator of this one. So similarly, for any arbitrary inc-invariant ideal, there always exists finitely many member in R, where you can obtain all the entries by applying the inc operator on those n. So this was the result which gives you a complete idea about that is the fundamental finiteness theorem in this particular theory. And here are the main references. So this is a book or a proceeding chapter, and a brief survey on asymptotic behavior of symmetric, a brief survey which was published in Commutative. This is one of the proceeding book, and this appeared in 2020. And then there is a reference of Uwe Nagel and Tim Romer on FI and OI modules. So this is the starting paper which appeared in Journal of Algebra. And later on, there is another paper, Uwe Nagel and Tim Romer, where they were discussing about the equivariant Hilbert series. There you can find many counterexamples. So equivariant Hilbert series in non-Nadine polynomial rings. Again, this work appeared in Journal of Algebra. So anything which is going, so this area is widely open, and regarding to Zahid question, so is not product of variable, it is not going further. Zahid, would you please clarify what do you mean? So you mean that the product grows or not? Am I right? You mean the degree of the polynomial, the degree of the monomial grows or not? It will not grow. It will remain the same. So if you started with the quadratic monomial ideal, so it stayed quadratic, and the generators keep on piling up. This is the way the structure goes. Okay, the people who are working on combinatorial commutative algebra side, uh, yes, Kamran, I4 is always unique. In this case, in every case, by applying the ink operator, one has to take all the possibilities, and it is always unique. Okay, the persons who are working in combinatorial commutative algebra, um, okay, if okay, this chain will not end, Zahid. This chain will simply goes on, and one has to see the asymptotic behavior, how it grows. If you look at the result, nature of the results, what people obtained. So this is the nature of the result the people obtained, that the co-dimension grow eventually linearly, and it is mentioned in this paper that this is mx plus c sort of thing, and similarly eventually exponentially. So the growth is given in the form of exponent. So this is a kind of results the people are obtaining. Okay, for the people who are working in combinatorial commutative algebra side, so one can pick any class of graph, and you can build for you have this particular monomial ideal, and one can talk about I3, one can talk about the chain of the ideal which are coming for a particular graph, particularly maybe for Cohen-Macaulay-ness, whether if I3 is Cohen-Macaulay, what about I4, I5, in which cases the Cohen-Macaulay-ness property retains. And similarly, there are many, so if people started to study this kind of structure for the monomial ideals coming from simplicial complexes. So the similar kind of thing can be done for that. For simplicial complexes, the same problem translated into other terms. For a particular ideal, one can think of a simplicial complex associated to this ideal in three variable case, and then one keep on increasing the simplicial complexes by using the ink operator. So instead of the monomial ideal, one has a sequence of simplicial complexes, a chain of simplicial complexes. There one can think about exploring the growth of f vector, h vector, and other things. So this is the way the problems can take shape in this particular area. And the main references are these three, where this kind of results have been studied. So these are very recent, and this is again low hanging fruits for the one who would like to study and do the work in this particular area. So these are the main references for that. That's it. Thank you very much.
Excuse me, sir.
Yes, Haris.
Yeah, sir, this concept, is it somehow related to graded modules and graded rings? Like, if it is like, then how is it related? Like, it looks
Um, uh,
almost,
okay, the graded ring or graded module structure is a particular case of this one, because this is a kind of grading, you would say. Uh, More or less, I would say this is the concept which is related to directed system. Okay, this question is very good, and the graded structure exists in each step you can think of. So R1 is a graded ring, it has a grading. R2 is a graded ring, it has its own grading. Rn is a graded ring, it has its own grading. But you can't have this kind of thing कि R1 को R2 से multiply करें, you will be in R3, or you understand my point? This
yeah,
kind
yeah,
of thing,
yeah,
this kind of thing is not there.
yeah, right. So
And
R1 into,
regarding to grading, you have this strict direct summand. You understand? So you can decompose R into the direct summand of R1 plus R2 plus O plus R3 and
yes,
then so
yes,
on.
yes, yes.
But in
Understand.
this case, we don't have. There is a union, not the direct summand.
Correct, yeah, yeah.
Okay.
Okay.
And to be very honest, I have no work in this area. These are few papers I came across, and I think of discussing this idea with others, and just put my hand on in this talk to present this topic.
Are there any other questions from the audience?
Imran,
Yes,
hello.
yes.
हाँ जी, well, it's a very interesting class of ideals. दो तीन बेसिक क्वेश्चंस हैं. एक तो आपने वो नोथेरियन तो बता ही दिया, मतलब ज्योमेट्री में जाने के लिए. एक दो और कंडीशंस है. फॉर एग्जांपल रेडिकल कब होते हैं ये?
Simply open है. Everything is open, Sohail, in this particular direction. Even a simple property is quite difficult to handle in this case. For instance, one can think of, if you started with the radical ideal and then you keep on going, whether the upcoming class is going to be the radical one. Again, I am not sure with the answer, and probably you will not find any, probably. So this is widely open, and ultimately one has to come up with the answer. Okay, one has to come up with its own way of defining things. So one has to redefine the things, the radical and other things. But the geometrical aspects are, the people are working on geometrical aspects of it. A lot of studies going on in algebraic geometry group, where the people are discussing the varieties, and you have seen the paper of Cohen. He was discussing a similar kind of thing, but this was quite past. Probably there would be some development in that area too. Where is the paper of Cohen? Probably you will see something in this particular paper on the laws of Machiavellian variety, where he might has considered the algebraic geometry setting, variety setting.
Okay, thank you.
Thank you, dear.
Any other questions? If not, let's thank Dr. Imran for sharing his invaluable knowledge and expertise. And thank you everyone for joining and making this a successful series. Thank you, Allah Hafiz.
Thank you everyone. Thank you, Dr. Shahina.
Allah Hafiz.
Allah Hafiz.